All right, everybody. We've made it to what I believe will be the last play posit on new material this year. Take a moment to silently let a tear roll down your cheek. And then let's go. Okay, so we are going to be continuing differential equations. The previous two videos have been about what is a differential equation and how to verify a solution that's given to you to see if it works in a certain differential equation. The last one was about slope fields. Now we're actually going to look at if you are given a differential equation, how do you just solve it to figure out what the general or particular solutions are. So here we're not going to be given a potential solution. We are going to find the solutions. Okay. So there are a lot of different types of differential equations out there. You can take a whole semester courses in college about different classes of differential equations. We are only going to be looking at a very specific type of differential equation in this class. They're called separable equations. They're called that because we can separate all of the x's to one side of the equation and all the y's to the other side of the equation. So hopefully this will just be your first sample of differential equations, and as you move on in your math career, you will see a lot more. But we're going to start with a pretty simple one. And for all of these problems, we're going to follow a three-step process. We're going to rewrite the problem, we are going to separate the variables, and then we are going to integrate both sides. So here, in this simple example, we are trying to find the solution to the differential equation y prime equals 4 minus x. The rewrite step is very simple. Anywhere where I see a y prime, I'm going to replace that with dy dx. Y prime and dy dx mean the same thing. And now I'm going to separate everything that has an x to one side and everything that has a y to the other side. This is very easy in this equation. The only thing that has a y in it is this dy. So I'm going to leave that on the left-hand side, and I am going to multiply both sides by dx. To be fair, this 4x should have a parentheses around it. So now I have anything with a y in it on the left-hand side, anything with an x on it on the right-hand side. This separation step might be more algebraically complicated than this particular example. We'll see some in a second. But this is the gist. We want to get everything that has an x on one side and everything that has a y on the other side. And we are going to break up that dy dx so that the dy goes on the y side and the dx goes on the x side. You always want to separate it so that dx and dy are not in the denominator of anything. If you end up with something like 1 over dy on one side and dx in the denominator of the other side, you basically just want to switch sides, move the x's to the other side and the y's to the other. And then finally, we're going to integrate both sides. So I did the integration on the next slide. On the right-hand side, we are basically, the left-hand side, we're basically integrating 1 dy. And then on the right-hand side, we are integrating 4 minus x. When you integrate 1 dy, you get y. And then when you integrate 4 minus x, you get 4x minus x squared over 2 plus c. And that's it. That is the general solution to this differential equation. So remember, the differential equation was y prime equals 4 minus x. If we go ahead and check this, we will see that the function we came up with is in fact fits this differential equation. If I take the derivative of the solution we got, I just get 4 minus x. The c drops out. C could be any constant. That's why it's the general solution. And there we go. It works. That was it. Done and done. So here's an example for you to try. Find the solution to differential equation x times y plus y prime equals 100x. So this one's a little bit more complex, but not too much. So go ahead and let's rewrite this, replacing y prime with dy dx. So x times y plus dy dx equals 100x. Step 1, check. Okay, so now I want you to try to separate this so that you get all the x's on one side and all the y's on another. This one is an example of one where the separation step is a little bit more complex algebraically, but I have faith in you. Go ahead and try it, and then I'll explain how I did it. Okay, so here's how I did this. The first thing I did was I subtracted xy to the other side to get dy dx by itself. Also, I was collecting any term that had an x in it. Then, over on the right-hand side, both these terms have an x in them. So I am going to factor that out. So this happens a lot in these types of problems, where when you gather terms on one side, they each have the same variable in them, and you can pull that out. So in the next step, I get x times the quantity 100 minus y. This is cool because now I've separated the x and the y's in a product, and I can now move them around. So I am going to multiply this dx over to the right-hand side. That's this step. And then the last thing I did was divide both sides by 100 minus y. So on the left-hand side, I get dy over 100 minus y equals x dx. So this is what I was talking about earlier. When you get to this step where you are starting to split up the dy dx, notice I multiplied the dx to the other side because I want to keep the dx and the dy in the numerator of things. So notice I have dy in the numerator here. Using multiplication and division, there is a way to write this equation so it's 100 minus y over dy equals 1 over x dx. You don't want to do that version because your dy and dx are in the denominator. So if you ended up doing that in your algebra, make a note. You want to aim to get this separate this equation into a form where dy and dx are in the numerator and not in a denominator. Okay, so anyway, now I'm on step 3, which is integrate. So now we need to integrate dy over 100 minus y. And integrate the other side, x dx. So I'll give you a second. You can just treat each side separately. That's why it's called a separable equation. And we'll see where you get. Okay, so the right-hand side is obviously easier to integrate. That's the answer on the right-hand side. Let's go ahead and now figure out the left-hand side. Okay, so the left-hand side actually almost fits the natural log pattern. In the numerator, dy is almost the derivative of negative y. The only thing missing is a negative sign. So I'm going to multiply by negative 1 inside and outside of the integral. That will give me negative dy over 100 minus y. Then I do have the pattern of derivative over original expression, and it will integrate into natural log of the denominator. So that's what I get here. This is a fine way to leave the answer. You could also rearrange it however you want. X squared over 2 plus natural log of 100 minus y plus c equals 0 would be fine. As long as you get to here, that is the solution to this differential equation. Okay. So sometimes you'll see problems where they will describe a differential equation to you in words, and you have to write the equation and then solve it. So here is a problem about beehives, I guess. So the rate of change of the number of bees with respect to time. So I see the word rate, and I see with respect to time. That is a giveaway that the equation I'm about to write should be the equation for a derivative. Derivatives are rates. So the rate of change of the number of bees, so dB with respect to time, dt. So that is this first phrase. The rate of change of the number of bees in a hive with respect to time. So that's dB dt is proportional to, so I'm going to have a constant of proportionality, the square root of time. T will be time. So dB dt is equal to k times square root of t. That is what this description is saying. So the rate of change of the number of bees with respect to time is proportional to the square root of time. This is pretty simple to solve. It's easy to separate. We just need to multiply the dt over to the other side, and then we'll have b's on one side and t's on the other. And then we'll integrate. And you get this little solution. that the number of b's at a given time is 2k over 3 times t to the 3/2 plus c. So this is a general solution. If we were given more information, we could figure out a particular solution, but that is the general solution. So sometimes, most of the time, you're going to be actually given a differential equation to solve. Sometimes there have been word problems up there where a situation is described in words and you have to write the equation for a derivative and then solve it. Okay, so here's another example of where you're given the differential equation and you have to solve. So go ahead and do the 3 steps. Let's rewrite, separate, and integrate. So go ahead and rewrite this so that y prime is replaced with dy dx. All right, so we get dy dx equals 2x over y. Now go ahead and separate it. So figure out what you get when you separate the 2 variables. Y dy equals 2x dx. All right, that's what we get when we separate. This is a pretty easily separated example. And now we just want to integrate both sides. So bloop, bloop, integrate, integrate. Go ahead and figure out what you get when you integrate. Okay, I get y squared over 2 plus c equals 2x squared over 2 plus c. So these are actually different c's. So I'm going to get y squared over 2 equals x squared. And we can combine these 2 constants of integration into a single constant. Technically, the constant you get on both sides could be different numbers, but you could always subtract one over the other. So when we're doing differential equations, you will always see in the general solution that multiple constants of integration are just rewritten, captured into a single constant of integration. So there'll always only be one c. Okay, so this is the general solution. We can rewrite that if we want. Who cares? Okay. Okay, the last part is we need to find the particular solution that goes through this specific, whoa, that's not the highlighter, this specific point, 2, 3. No problem. We're just going to plug in 2 for x and 3 for y. We get 3 squared over 2 is equal to 2 squared plus c. That's going to give us 9/2 equals 4 plus c. And you get that c is 1/2. So our particular solution is y squared over 2 equals x squared plus 1/2. And there we go. All right. So that's pretty much it. So rewrite, separate, and integrate. The trickiest part on a lot of these problems is the separation step, just remembering your algebra for how to do it. I actually don't know if those page numbers are correct. It might be from a different edition of the book, but I'll put up some practice problems on Haiku. All right, y'all. This is it. Signing off from PlayPosit. Thanks for listening. Good luck with AP Prep. Bye.